If you're new here, then this is basically the introductory notebook from the Quera Quantum Challenges. It's the one that's posted in resources. Um, but
Yeah, so to just like run this code, you can either use like Google Colab or you can like download these packages on like VS Code or something. So just make sure you import all this so that we can get started with the code. So this portion of the code over here is basically importing these different these are the two noise models that we're going to be using to analyze how the noise affects the circuit that we're looking at. And yeah. And the difference between these two noise models is that the Gemini 1 noise model deals with the case where all the operations on the qubits are being done within one particular entanglement zone. And the Gemini 2 zone noise model is basically where you have the storage zone and an entanglement zone. And whenever you want to perform an operation on these qubits, you have to move each of the neutral atoms into the entanglement zone to do the operation on them. And there are different types of errors that you can encounter with these. For example, in the Gemini 1 zone noise model, you can have unpaired atom errors where you are trying to entangle a pair of qubits, but then there's your other qubits in the entanglement zone that are unpaired. So you can have errors due to that. You can have mover errors where the qubits themselves decohere when you try to move them. And in the case of the two-zone noise model, because all the other neutral atoms are sitting or not doing anything in the storage zone, while you're doing operations on the other ones, they can also decohere during that time. So you have all these errors that can play into your circuit. So these two models are what take into account those errors.
quantum information, qubits tend to get lost because they're atoms that are being held by these optical traps. And even besides that, they just tend to lose their information after a while, especially entanglement, which is when two qubits are tied together. So you have to kind of try and get these operations done quick before you lose them.
Mhm. And this piece of code just is initializing the simulator for the circuit that we're gonna build. Over here, we're just defining the qubits, and the sort.line qubit is basically just this method that allows you to find how many qubits you want to be in your circuit. So if I like change the range to 3 or some integer, depending on that, I can define what the number of qubits that I'm gonna use in the circuit. So, and this circuit from moments part is just going to be defining the circuit that you're going to draw, right? So at each moment, it's basically giving you the instruction to apply some gate on the qubit 0 and then some gate on qubit 1. So in this case, in the first moment, you're applying gate X on qubit 0 and applying gate Y on qubit 1. And similarly, you can see like all the different operations that are being applied on both these qubits over these 4 moments. And this is another circuit, which you can see the diagram for over here. So in moment 1, you can see that there's a gate Y being applied to qubit 1. So that's why there isn't any operation on qubit 0 at that moment, and only the gate Y at qubit 1. And then in the next moment, you can see 2 X gates being applied to both the qubits, and then 2 Y gates on both qubits, and then the 2 X gates, and finally the Y gate on qubit 0 over here. So this is a diagram, and we run this code again to help you guys see how the first circuit is going to look like. second. So you can see that the output basically describes what we have in the circuit over here. So XY, YX, XY, and then YX. So they're just alternating back and forth in each qubit. Okay. So now we're going to be modeling the noise on a particular circuit. And in this case, we're going to be, we can model the noise on either this circuit over here, the one that we just displayed a picture of, and the other one. The other one's going to be used for global gate operations, and I'll get to that in like a few minutes. So we have to define what our X gate is and what our Y gate is. So in this case, the circ.phased XZ gate is basically just defining the gate itself as like due to some phase rotation in, like, you can think of it as being some phase rotation in the block sphere. So
Basically, Circ lets you define your own custom gates because you can just do any arbitrary rotation around the block sphere. You can just tell Circ, hey, I want to do a rotation around the XZ axis by this much.
and over here, if you have the X exponent, so the rotation around the XY plane is going to be some angle phi, and then the rotation from the positive Z axis to how do I say, about the other axes is going to be some angle theta, right? So in this case, the X exponent is just or the phi in this case is just equal to I times the X exponent, and the Z exponent is equal to the Z exponent is going to equal to, sorry, not the Z exponent, the axis phase exponent times pi is going to equal phi, and then theta is just going to be pi times the X exponent. So if you want to rotate the state vector by some amount pi, the X exponent is going to be equal to 1. So because when you're operating on a qubit using an X gate, what it's essentially doing is it's taking it from the from ket 0 to the other state. So it's doing a pi rotation about the X axis. And for the Y gate, it's essentially the same idea, but you can imagine the vector going from like the X axis with a pi over 2 rotation in the XY plane, and then a pi rotation downwards. So we're just defining these gates customly using this. So over here, we're defining some arbitrary gate that's like similar to this gate that we saw above over here. It's just that the XY one second, let me like print it out so it's much more. So these portions over here, we can see that they're for qubits 1 and 0, the same gates are being applied. So over here in moment 2, there's X and X being applied and Y being applied. So we can see that through this function, we're essentially doing the same thing, but then it's just that we are allowing that XY portion to be, we can implement it however many times over like however many moments we want, depending on whatever integer you choose for the function itself. And this is going to be the case when we're using global gates. So the idea of a global gate is basically where you're trying to apply one laser pulse to multiple qubits just so you can minimize the error. Local gates is basically where you try to apply a gate on a particular qubit, but it ends up increasing the error compared to a global gate because you want your result to be in some particular state, but then due to like external noise, it's going to be deviated from that state. But then when you're doing a global gate, you're applying the same laser pulse on multiple different qubits, but then even though they're not exactly aligned with the state that you're expecting, they're in the same direction. So comparatively, there's like much less error that you get.
Basically, the idea is that if you're going to do a bunch of local pulses, there's usually a tertiary abstracted gate zone where you have to move these qubits into. If you do a global gate, then you just shine them even while they're in storage, and you can just like each of these gates that are these rotations on the blocks here are applied via laser pulses in this kind of computer. If you need to do a local gate, then you have to move this qubit away into its own little zone, flash the laser, and move it back. In this process, you can lose the qubit. If you do a global gate, not only do you reduce the amount of time that's taken, because instead of doing one pulse, two pulse, you can just get them all to a pulse at the same time, and you get less mutual error because they're now, even if some error happened, they all now share that same error. And because these are all rotations, it doesn't really matter as long as the rotations are all the same.
Yeah. So in this case, the function will, the defined function will run this part of the code if we are using global gates, and then if not, we're just gonna get the previous output that we had for cell. So this is basically defining our circuit, and then we're just like printing out the circuit using the Gemini 2 zone noise model. This is going to give you the errors associated with like each operation, and we can see over here that we have our circuit defined by the X gates and the Y gates. And then in the bottom, we can see the different errors associated with applying each of those gates on the qubits. Certain moments.
Oh yeah. So just one thing to note, the noise model is just dependent on the architecture because it's literally just like, hey, if I put all of these qubits in this configuration, what's the noise rate that I'm going to try and expect? That's why it's independent of the gates, and you just load it up depending on what architecture you're using.
So this is the output you would get when the global gate's set to false. And then when you set it equal to true, we can see that our original circuit is basically the one that we got in the previous output. And the associated errors are just the errors that you would get when applying the global gates to that particular circuit. And you can see that like the errors are much lower compared to the previous ones too on each gate. This was like 0.00307, but for the previous one, it was 0.00806. So we can see that the error from a global gate is much less compared to just applying laser pulses individually at each cube.
See that there's like a lot more increased parallelism. The circuit depth itself has decreased, and the concept of circuit depth is basically saying, hey, I have my qubit, which I'm hence the name line qubit. I have a bunch of operations I'm going to do. And when you do operations in parallel versus like, having this one all the way out here, the amount of time it takes for the entire thing to complete is reduced, just like in traditional computing.
And in this cell, we are trying to plot the fidelity. So basically what we're trying to do is we're taking into account all these errors on our circuit. And then what we're trying to do is we're trying to measure. Okay, let me like explain through the code so it makes more sense. So over here for them. So we're defining our circuit over here. And the local circuit is basically where we're not applying global gates, and the global circuits where we are. And we're applying noise on the circuit. And then after that, what we're doing is we're running this multiple different times to see our distribution of like what different vectors that we get. And then over here, we're just like calculating the probability of measuring the zero or like the measuring ket zero, and we're dividing it by the total number of values that we get when doing those repetitions to see how many actually do match up. So
Chuck, do you wanna show what fidelity is on the blocks here?
on blocks here.
Yeah.
So let's just say like this is ket 0. This is ket 1. Let's just say you're doing some kind of measurement, right? So
You might wanna step outside so they can see.
yeah. Let's just say that when you measure, you have a vector that's like over here. it's not necessarily aligned with the get zero vector because there's noise in it. And what we're trying to essentially do is measure this multiple times to see how many of our measurements out of the total measurements we make are aligned with this. So by doing that, we can see but by doing that, we can basically like plot this out. That's basically what the code does. And using local gates, we can see that comparatively the error is much, much less compared to local gates because as Mihir was explaining before, all the qubits are essentially in the same direction, even though they're not necessarily aligned with that particular statement. And with the local gates or the local pulses being applied to each qubit, the total error is going to be much, much greater. So as you increase the number of qubits, the errors are greater when comparing to the local gates being applied at the same time on multiple qubits.
The idea is basically just, hey, we're going to run a toy circuit to test this out. So it's just going to do, for all the qubits, it's going to do like, hey, I'm going to do like this rotation over here. I'm going to rotate it here next. I'm going to rotate it around here. I'm going to entangle these two qubits. And I'm going to rotate them both like correlatedly in this thing. But the idea is that at the end of the circuit, we're just trying to like return them back to initialization, taking the really, really long way around. Because, yes, so you can see in the global and local gates, other than this one jump here for whatever reason where like some error canceled itself out, each of these circuits tends to accumulate errors as you go along the depth, which is just like the gates that we're doing. And the global gates accumulate far more error than the the local gates accumulate far more errors than the global gates do. This fidelity is essentially saying, hey, if I have my ket zero and I have my final state vector, what's the cosine similarity between the two? Oh,
Good. Is the fidelity decreasing anymore on the global line?
It is decreasing, but compared to applying local gates, it's not decreasing as fast. Because with the local gates, as you increase like if you have like 10 qubits, right? And then you're applying an individual laser pulse to each qubit to perform some operation, what happens is they're all gonna have some error and then they're all gonna accumulate. But the thing with global gates is you're essentially like shining one single laser pulse through all the qubits. You're doing like the same operation, even though you're gonna have some error with all of them. It's not going to accumulate like the local ones because they're essentially like pointed in the same direction, if you know what I mean. Right, that's
so you get like less of these like entangling errors because now I have some guarantee on like, how close are these two going to be when I measure them both at the same time once they're entangled. But you also just get the speed advantage, right? Every time I shine a laser, there's a chance something goes wrong. So if I do like a bunch of like local gates, then there's something going wrong in each of those, even if it's not the qubit I'm shining the laser on, right? Because these are like physical lasers and these are qubits, I can shine a laser on this qubit, some can reflect off, change the state of this qubit slightly. And also, there are just like, like electromagnetic rays everywhere. Even just having this qubit sitting around while its body is getting operated on, it's going to accumulate some error.
This might be a really basic question, but with a global laser where you're flying into all the qubits, you don't make all of them kind of coherent with each other, lose information.
You do make them cohere, right? So obviously, like the architects know that, there's going to be some kind of scattering and whatnot, right? So, but what you can do is you can calibrate the laser for that, and you can just have it be like, hey, like I'm going to synchronize it for this, whatever this pattern, the current pattern is right now in the zone, and I'm going to try and minimize that error. If you're doing local gates, right, it's just a bit harder to do that because now you have to compute all these local operations. Yeah, like for example, right, if I have like qubit one, qubit two, and I'm going to set these both like the Hadamard states, like half zero, half one, over here and over here. And then I entangle them, right? And then I say, hey, I'm going to measure this in the Bell basis, which is basically just like get zero, get one. And I want to guarantee the same answer from both of them. If I do this locally, then I can get some error where it's like, oh, like this one ends up over here, this one ends up over here. And then there's a higher chance I get an anti-symmetric measurement, right? which just like should be nonsense. I shouldn't even be able to get this kind of answer. But even if if I do a global gate and there is some error, because they're both guaranteed to kind of be in the same plane, the answer is still the same, right? The correlation is kind of still the same.
So in this piece of code, what we're gonna basically do is analyze the circuit by applying CNOT gates, and then this log depth essentially just means that like when looking at the circuit itself. So when running this, what you can see is that for some number of qubits, the pattern of applying the CNOT gates is gonna look like a log. So we can see like trace it over here. So it's 1, 2, 4, and then after that you're gonna have 8, so on and so forth. But in this case, we're just like analyzing the error using this model. So when applying the CNOT gates, when you're trying to entangle the qubits, what the problem you're gonna have is that there's also error when trying to do that. So in this case, you're gonna get a combined state, which is called the GHZ state. And then there's technically supposed to be a 50-50 chance of measuring ket 0 and ket 1. But then because there's error, there's obviously gonna be some deviation. So we're just trying to like use this model to take into account the that's caused by.
The GHZ state is basically just like what we exactly talked about here, right? I want them all to kind of point in like the same direction of like 0 or 1. So when we say ket 0 or ket 1 in this context, it really just means, oh, all of them are 0 or all of them are 1. We want them all to have that same correlation factor between them.
In this case, we can just like see the diagram of the circuit itself. And over here, we see that the one zone model actually has much less overall error compared to the two zone model. Yeah. That's because of like the log behavior of the graph itself. That's why you can see like the steps down. Yeah. Like, you know, like we're implementing like the whole circuit in like a log depth, right? So over here you can see how the number of CNOT, like the way the CNOT gates are applied themselves look like a logarithmic pattern, right? And it's because of that logarithmic pattern that you're getting those like steps down in the graph itself. Never makes sense.
You go back to
Last
circuit.
one,
Yeah.
why does log,
Yeah, just go to like this,
Oh.
look at this thing. Yeah, if you look at like some other different circuits, then you can see that like, the GHZ state is just mildly good, that like, the idea is like, oh, you have to do 3 at a time. It's like, it's like 3, then 4, and then like 5, and so on and so forth. As soon as you get like that initial like 3 step, right? That's how the logarithm is kind of growing. So that's kind of where that error comes in. It's also a little bit niche because now this is kind of like getting into the actual like movement and like how we're doing this. Why do you think the two zone model performs worse here versus before? Any hypothesis?
Let's see. I'm assuming it's probably because of okay, but it's probably because of mover like sitter errors, right?
Yep.
Because you have to move each qubit into the entangling zone. And then based off of the pattern, you're doing like 2 CNOTs, 4, and then 8. So there's gonna be like all those other qubits just sitting there, and then they're gonna like decohere.
Yeah, exactly. Entanglement dies down over distance. Just because we have these qubits like split up between 2 zones instead of 1 zone, it's just harder for them to entangle. Because if you want to entangle 2 qubits, then you actually kind of make use of this backscattering. You have to physically bring 2 qubits together, and then you shine a laser on them at the same time, and then you use the scattering interaction between the two to entangle them. Oh yeah, but do you want to explain why this gives us an advantage over other architectures?
The two zone?
No, just like like the ion trap versus neutral atom. Okay, I'll do it. So you might have heard of IonQ, which is Maryland's kind of like homegrown quantum computer system. Those use something called ion traps, where you just have all your qubits, which are ions, sitting in a line like this. Now, suppose I do like, whatever local operations, I do like, one operation here, one operation here, one operation here, yada, yada. But now I want to entangle these two qubits.
You have to entangle this qubit. After that, you have to entangle this one and this one, this one, this one, this one. You gotta like do it consecutively in order to entangle the first and last.
Yeah,
So it just takes a lot of time to do it.
it takes a lot of time and it causes a lot of errors because entangling gates are basically the most expensive kind of gate in just in terms of errors, right? So just having to like propagate it here, 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 here. It's still a lot worse than just grabbing like one qubit here, moving them together into a different zone, and then entangling them and then moving them back. So this non-locality of operations is what kind of makes the architecture so powerful.
Over here now, we're just gonna look at the qubits themselves and how we can move them in like a grid like manner and how to minimize the total number of moves, because the more moves you take to perform your operations, the more error you're going to accumulate. This includes just the qubits sitting in the grid and also the qubits that you're moving, because they all decohere very fastly, and that's why.
I'd also just like to point out, if you look at that conflict graph model, this is kind of one of those preset methods. But if you're like a CS major or you don't know too much about quantum information, this is still like something you can do. The idea here is essentially just like, hey, I have a sequence of all of these moves depending on the geometry of the model. What's the optimal way to like sequence them, right? What are all the ones I can do in parallel such that like it's condensed as fast as possible for this circuit. And it turns out that you can reduce this to a graph coloring problem. Hence the conflict graph.
So in this case, this code is basically like telling you how many moves, the minimum number of moves it would take for you to compute all the operations on this particular grid of qubits. So for the first geometry that we have, let me pull up a picture so that helps. So we can see this is our first configuration. And based off of this and the operations that we need to perform on the qubits themselves, it's basically taking into account the movement conflicts. Because the thing is, you can't really move two qubits across diagonally to each other. So if you want to take qubit 1 and qubit 3 and entangle them, then the qubit 0 and qubit 4 and entangle them. You can't move qubit 1 and 0 at the same time. You have to do one or the other, like one after the other. So it's basically this piece of code is basically just telling you the minimum number of moves that it takes to perform all these operations. And we can see that like with the
Minimum
other
number of parallel moves.
parallel moves.
Yeah, because the idea is essentially if you go back up,
Uh-huh.
if you try and move this one here and this one here at the same time, they're gonna smash into each other. You lost both your qubits. Congratulations. However, you can move, suppose like this one here. Oh wait, yeah. That. Yeah, you can move like 0 to 4 and 1 to 2 at the same time, but you have to do a coloring based on kind of which ones you have, what order you have to do the operations in as well, right? So this is what kind of where the graph coloring comes in. I can do this to this to this all at the same time, and I can do this to this to this to this at the same time.
In our second configuration, we can see that like this only requires 28 moves as compared to the other one. So So that's pretty much it.
So you can play around. We'll post
Mhm.
this notebook online, but obviously like
Yeah.
you can also just pick it up from the IEEE notebook, which you can find in the Discord under resources. And you can try like coming up with your own geometries to see how you have to see which ones work better and so on. Or if you can find an algorithm to just be like, hey, like this is the optimal geometry given um these positions, so on. But there's also just like more fun physicsy things to do, like like how close can I really move two of these atoms together before they just mutually attract or like mutually destroy each other. So yeah, I mean just go exploring on the GitHub. If you would like pointers from the officers, feel free to either just ping me or ping an officer, and we'll point you to like some of the more fun notebooks to try out. Yeah.
Yeah. Okay.
Any questions?
Yeah.
Hmm.
So you also test for, say, imaging, so flash images and test different areas in like the to organize them.
What do you mean? Sorry, like
Like it's like movements of like an image. So let's say you have like a stellar image that's in movement. You can test the different pixels that are moving at its time.
I'm not sure I quite got it. So, like, okay, so you have like some kind of like bitmap image, I'm guessing. And then, okay, you have pixels and you want to check for pixel movement.
Based off like the like geometry defining it later. So we can look for different like pixelization movement.
For the graph conflict?
Yeah.
Oh, okay, yeah. I mean, like, okay. So this is fortunately actually one I had to program at coincidentally I quack because we we actually worked on the same problem, but the idea is essentially just like, oh, like, suppose I have all these moves, right? Okay, just some like arbitrary number of moves or things like that. Basically, I'm going to create a graph that has every single movement, right? So I'm going to name this move one, this move two, this move three, this move four, so on and so forth, right? Whatever your actions are, so to speak, you just enumerate them one to n for n actions, right? Yeah. And then from those, oh, this will get mildly confusing just because how this works. So now you have like all of your actions and you just point them into like the nodes of a graph, right? Now, for every single action that has to happen at the same time, right? So suppose like I know for a fact that just because of my circuit, this action has to happen at like time frame one and time frame two, right? It's like on the same qubit. If I have this action and this action, they have to be disjoint, correct? So for each of these, you can draw a fully connected graph just by like drawing a line drawing an edge between these two. So suppose this is like, this is action one, two, three, four, five, and so on. For any two actions that are like disjoint, you can draw an edge, or you can just build a smaller graph and just say like, hey, I'm only going to consider like this time step because that's what matters to me, right? And then you can have a small graph with just these nodes. But each of these nodes then represents each of your like actions and so on, right? Now you check each of these nodes pairwise, and you just say, hey, if any of them conflict, right, they can't happen at the same time, I'm going to put an edge between them. Everybody clear so far? I know it's a little abstract with like, where I'm, but I promise I'll get to the point. But yeah, so the idea is all of your actions become nodes, your edges are the conflicts between them. Now you just do a graph coloring. Who knows what a graph coloring is? Okay, so graph coloring is one of the more famous NP complete, yeah, NP complete problems, which is basically just like, oh, like, I want to, given a certain number of colors, right? Usually two or three, sometimes two colorings, sometimes three colorings. In this case, this is just like I think this is three colorable. Yeah, I think any graph is three colorable. No, that's not true. Sorry, give me a second. Yeah, any graph is three colorable, I think. or n-colorable, but like that's not the point. So the idea is just like, hey, I'm going to assign a color to this node, right? Like this is going to be a red node. If suppose I have like a 3 coloring, like this RGB. Any two adjacent nodes cannot have the same color. Because this is an NP-complete, you can't exactly solve this. Essentially, like, there's no like exact algorithm that'll guaranteed solve it. You just have to like kind of like try different ones, but we have very fast ones just because this is a very common problem. Once you have all your colorings, right? It's like, like, oh, these can share a thing. These can share things. I'm going to do blue for this. This can share red, but green is free, so I'm going to assign it green. Now, all your actions that share the same color, you can do at the same time because they don't conflict. Because if they conflicted, they would have an edge between them, which means that they can't have the same color. So now you have all your parallel sets of moves. You just pick like, hey, like depending on like time or like, whatever other category you have, you just say like, hey, I'm going to do all the red ones first, all the green ones next, all the blue ones next, so on and so forth. Does that answer your question?
Yeah, it's really interesting how you said it, because it kind of about the K cluster meaning for machine learning.
Yeah.
Is that visualization, you're gonna get all of the forces.
You can actually reduce it to, there's actually a very fun way you can reduce like K clustering to a graph coloring. And then you use like a graph coloring solver to solve K cluster means. Just because it is NP complete, you can't just reduce anything to it technically. But yeah, there's more direct reduction. Sorry, you're saying?
Oh, no, that.
Oh, that is it. Okay, yeah. But yeah, I mean, there's kind of more fun things like I was talking about the geometry before. If you have because this circuit is just an abstraction, right, of all the things you actually want to run. Another cool thing, or maybe uncool thing, depending on how you want to look at it, is that you don't actually get all of these fancy gates, right? You don't actually get like an XZ gate. Doesn't really exist. You get like you have these lasers and you can tune them, but usually they're just rotations on 2 axes because it just becomes more expensive or like more difficult to have in both. So the idea is like, oh, I have like some arbitrary X rotation, I have some arbitrary Z rotation, and you have some basic gate set, right? Think of them like the ands, ors, nans. Oh, no, yeah, whatever, like nans in like computer science, like you have some basic operation that you build everything else from, that you build like a for loop from. So you have to like compose these together to build all these other operations. So if you go back, control of native gate set. Yeah, cool. So if you enable this native gate set equals true, then you'll see a completely different circuit just because it has to compile it to this native gate set first. So this one gate will turn out to be like 5 or 6 or something. That's why, like, on all these quantum circuits, like, even if you're doing like an IonQ computer, you'll just see like a C naught from here to here. You won't actually see like this intermediate chain unless you compile to a native gate set. So just based on the geometry or like based on this, you can just be like, hey, like, how do I optimally compile to the native gate set just by doing these decompositions? And that's all just like matrix math. Or you can be like, hey, given this circuit operation, what is the optimal initial arrangement? Or like, initial assignments, because what qubits are local to each other is again another big problem, right? If I just do 1, 2, 3, 4, 5, and qubits 1 and 5 interact all the time, and I just do like 50 entangling operations between them, and just like one interaction between everything else, and 1 and 5 are like over here, then that's a problem. Yeah, so like there's just like a lot of fun problems and things to solve here. There's even this thing called like quantum scarring, where like if you move a neutral atom, depending on the dynamics of the array, it can leave like a trace that's just like sits there for the rest of the operation. There's a paper out on it now, I believe, or it might be in preprint still. But yeah, so that's another like, if you're just interested in the physics of it, then you can just go analyze that. Quantum scar. Yeah, listen, I only read like the beginning of the paper. It's like, oh, like, or is it, oh yeah, if you move like a neutral atom through, then like it perturbs all the other things in the way slightly. Because they're in like AOMs, right, which are just like laser traps. there's something like, like, oh, like it keeps shaking afterwards. Just you added some oscillatory movement to each of these neutral atoms. And that leaves like a scar on your operations. It was a lot of math. I just read like the paper, I was just like, oh, this is cool. Yeah.
Do you know what that is?
Just look, it actually came out of a hackathon challenge, which I think the analog of is actually there's a notebook corresponding to that in the GitHub. But if you look up just like quantum scars Quera, it might come up. But yeah, so like if you find that interesting, you can just like experiment on it here. And like, if you get like some decent work done, or even if you just want to like phone up like, Pedro at Quera, and then, you want to write a paper on that, then you can probably just join. Yeah. Yeah. Look up quantum simulation. Oh, wait, but no, sorry.
It's kind of random, but
Hmm.
if the atoms weren't neutral, it would remind me of like a super, like the phonon moving through at the higher charge areas.
Hmm.
Sounds very familiar. Like you get Cooper pairing or something. You know what I mean?
I mean, that's how superconducting qubits work. Because Cooper pairs can be, because something like some insane number like 5 million Cooper pairs can form a qubit in like a superconducting circuit. So I mean, that's how that works, but I don't know, maybe there's some mutual coins there. I'm still in quantum too. You'll have to give me some time to catch up. Okay, it's still in preprint. Just ping me on the Discord. I'll see if I can find it and send it to you. Or I can just ping Dimitri. See how far along he is on it. Okay, yeah. Hope everybody had fun. We will have this showcase December 11th. So you have until then to do whatever projects you would like. As always, the officers are here to help. The QRS Slack is open. You can ping the scientists there anytime. And they will help out there as well. They have office hours. So you can just show up to those or just ping them and just like take it, restart up at the end. Yeah.